Thank you, Marco, for a great intro and the kind invitation to come and talk to you guys this morning. So my background, for those of you who don't know, is that for many years I was professor of physics and then later professor of computer science. And I've sort of dedicated my career to trying to understand the science of operations. I got involved in managing computers quite early on, as you do. It occurred to me that I could apply some of my knowledge of physics and systems to the understanding of computer systems. It's a lot cheaper than studying the thing on your desk rather than going to Switzerland to crash particles together. So this seemed like a good idea. And then later on, as part of that understanding, I developed a program called CF Engine, which is some of you may know from configuration management history, and started the company CF Engine. A couple of years ago I finished that, and now I spend my life traveling the world, helping often bigger companies, but some startups as well, to understand what are the challenges of operations, how do we understand the science behind it, as well as just the sort of the business aspect of it. And one of the messages that I come across with is that ultimately what we want is predictability from systems. In order to be useful, in order to be available to us and satisfy a business purpose, we need predictability. And a lot of what I want to talk about today is about the lessons that I've learned from trying to understand how we can simply focus on the predictability of systems. How can we know when systems are working well? We often have a gut intuition of it. We may even have some rules of thumb. We read all kinds of blog posts about it, but very few people address it from the perspective of science, which is what I have tried to do, and I'd like to share with you some of these lessons that I've learned. When I originally posted the title for this talk, my friend Patrick Dubois said, how can we know when a system's working well? Well, it's when users are happy. And I thought about this for a while, and I decided that I didn't think that was a good enough answer, because people are happy for all kinds of different reasons. Some people are just happy to be here, happy to be in the game. Some people are never happy at all. And some people want to tie their happiness to certain measurable outcomes. So this is what I would like to try to talk to you a little bit about today. So what I've been looking for as a scientist, if you like, is a kind of an impartial language, a way of trying to describe these things. I'll tell you a bit about the journey along the way. But it's essentially, I think what we need is an attempt to understand and formalize some of the issues so that we can talk about them in a more technical or formal way. And the first thing you notice when you start trying to describe systems is it's actually quite hard to write down true statements about systems. Because systems are complex. They're complicated, they're mixed up, they have conflicting interests. They're trying to solve many different problems at the same time, keep people happy at the same time as save resources, be efficient at scaling. All of these different aspects of systems need to be taken into account. And to say something absolutely with certainty about this is quite hard. In fact, I will advertise my book later, which is called In Search of Certainty. So, apart from this other book, I've started this project actually in the last couple of years trying to write down some of the things that I've learned in a formal language. And this formal language is something that I call promise theory, which came out of trying to understand how systems make promises about their behaviors, about what we should expect from them, and to what extent can we ensure that they keep their promises. So a simple idea about how to understand functionality in systems. And if any of you are interested, this is the document. It's a work in progress, so it's not finished in any sense. And you may also be interested in this podcast, which I've started with John Willis, based on the same title as the book, but it's based on issues in this area. All right, so the 5 keywords in the title. How can we know that the system is working well? 5 things crucial to understand. Who are we, first of all? We is important because it's subjective, and it tells us that the evaluation or estimation or assessment of a system is a subjective issue. It's not an absolute objective thing that we can measure. And the subjectivity comes from the person, the user, making the judgment, making the assessment. It's not about what was intended. The intender of a service may have quite different expectations than the receiver of a service. So knowing that a system is working well is everyone has their own opinion on this, and we need to understand that. How about knowledge? What does it mean to know that a system is working well? Not just to think that a system, or feel that a system is working well, but to know it. And in this sense, I use the word know as we use the word know for humans. Knowledge management for me is about knowing something as you know a friend. And what do we mean by that? By knowing somebody like a friend, we mean that we meet somebody regularly. We see them every day. We learn their foibles, their characteristics, their behaviors. We know when they're in a good mood, in a bad mood. We know how to use that or avoid the bad bits. And having that relationship, that feedback cycle, enables us to make the best use of a system as we make the best use of our friends. We don't use our friends, of course. So the system, what is the system? Where does it start? Where does it end? Where is this, in this arena today, where is the system for me? Is it the stage? Is it my laptop? Is it the auditorium? Does it include you? Does it include the building we're in? Is it about London? Where exactly does it start and end? If there's a power failure in Greater London, we're dead. So is that part of the system, or is it not part of the system? Often we draw arbitrary lines around systems where we want to have dominion, where we believe we have control. And then we talk about dependencies on things outside of the system. So this is a crucial part of understanding what we mean by saying, if our system is working well, which bit is ours and which bit is theirs? What does it mean to say that it's working? How do we assess that? To what extent is it fulfilling its function? Is it fulfilling it well, just a little bit, 50%, 10%? Or can we actually say that it's fulfilling entirely the wrong function for the purpose that we intended to create the system for? And finally, well. How do we define well? Or good, as they would say in America. How do we quantify it? Can we put a number on that to say that it's working well? Can we even say that it's doing the right thing or the wrong thing? So these are the 5 parts of the question that I want to dig into today. So, system. What do we mean by system? In a system, I think the important thing to understand is that there are anything that works, anything that has some dynamical behavior is a balance between some freedom to operate, some space in which to move around, some parameters in which to operate, and some constraints, things that limit how much you can move around, how much you can explore the space of possibility. Some of these constraints are intentional, like security things, access controls, and so on. Other things are dynamical. We may not have enough power, we may not have enough CPU cores, we may not have enough memory. And understanding the behavior of a system depends very much on the ability to make predictions based upon those things. So is our system one thing, or is it many components working together? And if there are components working together, to what extent does the cooperation or communication between those parts play a role in how well the system's working? Now, there's an important point here, which is that that perspective on how well components are working together may be something that depends on our scale, the scale at which we make our assessment, and also the perspective that we have. So are we the provider or the user? That's clear. But what about if I am a human trying to figure out if the system is working well, and I'm getting my web page, it's coming back at me quickly, so I'm happy, I feel okay. But down at the level of the system, the scheduler is working like crazy. the system is thrashing like mad because actually it's not being able to handle its resource constraints very efficiently. And at a higher scale, we may have the illusion that things are working fine because we're pulling out of some cache. We don't notice the difficulties. But down at the bottom of the system, things are melting down and burning up. So perspective and scale actually have a lot to say about whether a system is working well. Today, we're talking a lot about microservices, breaking things up into small pieces. And I think it's one of those generally accepted truths or myths, if you like, of computer science that it is a good thing to break things up into modules, because modules are nice and tidy. And we all like things to be tidy. We're basically control freaks, right? Anybody not a control freak in here? Yeah, that's what I thought. But in systems, because you have components talking to each other, components are intertwined, they are entangled, they are commingled, they are, the myth that there is a modular structure to a system is often quite incorrect. Let me show you a picture which I think is, which sort of tells the story in my mind. On the left you have, Chinatown, anywhere, this is actually Hong Kong, but it could be anywhere in the world. Pretty messy, not terribly tidy, a chaos of things going on, people selling here and there in little corners of shops, everything's going on all at the same time, but very successful society. People getting along well, economy prospering. The right-hand side, a beautiful picture of architectural perfection designed by the so-called garden city planners of the 1960s and 70s. This is part of the architectural movement called the Garden City movement. And this is a map of Brasilia, I think, which was, somebody laughing already, which was designed to be perfectly separated. We will separate the housing from the shops, from the factories, because this is, good design, it's modularity. And we will connect them together by roads, just as we would a networker with, of course, a Cisco router at the center. But of course, this was a complete failure. Brasilia is clogged up with traffic congestion because it turns out that when you separate things so far apart, the only chance of getting there is to take a train or a bus. And of course, the more cars there are on the road, to do any little thing whatsoever brings the chaos of traffic congestion into full swing. And of course, the city sort of grinds to a halt. The city thrashes, as we understand thrashing in a system, because traffic congestion is holding up its efficient functioning. Whereas in Hong Kong, people just sort of roll out of bed onto the breakfast, and then they buy their stuff at the shop, and then they come back, they have their conversations, they go home. There's traffic congestion, but they're all free to move in a very small area, and the system is localized without being modularized. So there's a big difference between localization, which is a thing which brings efficiency because you don't have to travel very far to get what you need, and then modularization, where you may be trying to actually formally separate things and put it barriers and protocols and communication stacks and so on, and require an additional transportation service to get in between them. So this is, I think this is one of the sort of red herrings and myths of computer science, that we are taught modularity is a good thing, but in fact, when you get to the operations, it looks good on paper, but when you get to operations and you see it in practice, actually often it falls flat. So, things to understand about systems. Bunch of stuff which led to my investigations of dynamics and promise theory. First thing is, what do we intend? Systems are built for a purpose. So what do we intend by the system? What does the system claim? What does it claim to do? Or in my language, what does it promise us? Is it fit for purpose? This is the basic starting point. Then what is actual about it? What can we measure? What can we assess as an outside user or as an inside user? And at what scale? In other words, how do we know if we're succeeding? The goals of the system are pretty subjective. My goals might be different from yours. We go to the restaurant, everybody gets identical steaks. I think mine is perfect, you think it's too bloody or too well done. Exactly the same promise was made, but we assess it differently. And then a key thing about locality in a system, only the agent that makes a promise about its behavior can be authoritative about its intent. You can point to somebody and say, you should have done this, but if they didn't promise to do that, who are you to say? Similarly, when we expect things of systems that weren't designed to do what we expect of them, who is being unreasonable? To what extent are we being reasonable or unreasonable? And then, how do assessments change with scale and relativity and perspective? Are we making the judgment from inside the system or from outside the system, from the perspective of a user who is getting what they want or a user who's not getting what they want? So these are important issues. So I started trying to understand some of these questions at the end of the 1990s. I started a course at the university in operations. It was one of the first ones of its kind. And there was no textbook on the theory, and I wanted there to be a theory, because I'm a theoretician, essentially. So I wrote the book. I sat down and I thought, how can I gather together everything that's known about systems in all kinds of different fields, not just computer science, because actually computer scientists pretty much believe that the computer does what it tells you, what you tell it to do. We, of course, know that that's not quite true. So I wanted to put together as many things as I could. I wrote this book and came up with a simple answer, which is that in order to understand scaling and interactions, we need to understand how things are arranged in space, networks, and so on, distances, and how things work in time, how fast, how fast, how often, and so on. Clearly, the first thing that came out of this was that systems are not deterministic. We may decide to double the speed of something, doesn't mean that it's going to double. We may hope that requests will arrive at our web server in a nice regular order at different times of day, but in fact they come in bursts completely non-predictably. So unpredictability or indeterminism is a hugely important thing to be able to understand, and if we don't have models that can take into account indeterminism, we will be losing out. So we get to this question, how do we know a system is working well? So there are two ways in which the system can be working well. I call these dynamics and semantics. Dynamically, a system is working well if it's going fast enough, if it's getting to us in time, if it's meeting our needs on a just-in-time sort of basis. Semantically, it might be working well if it meets our expectations of functionality. Is it doing the right thing? Is it fit for purpose? Two quite different things, but the crucial thing is that everything that's semantic rides atop the things that are dynamic. If the system cannot deliver, then it cannot deliver the right thing or the wrong thing. So dynamics make no judgment about right or wrong, true or false, semantically fit for purpose or not fit for purpose. It's just, have I got anything to give, and can I even cope? So dynamics always trump semantics. And this is something that developers find extremely hard to understand because they're taught in university that things just work. If you program the computer, it just does as you tell it. And of course, when they're sitting on a laptop, a private computer with private resources, it's pretty much true. But when we connect things together in larger systems, bigger systems, try to scale them, those things cease to be true. So our expectations are often based upon assumptions. Whose assumptions are they based upon? Who is we? We are often the enemy. We've met the enemy and he is us, because our expectations are often wrong or incorrect. So when I got to this question of we, I realized that this initial book that I'd written on the dynamics of systems was missing a piece, and that was, what is the system supposed to do? Why are they there? What is the purpose? What promise do they try to keep? And originally I came at this from configuration management and policy, the idea of specifying what policy we intend the system to keep up with. Back in the 90s, this was sort of an unknown thing, but CF Engine was kind of an early policy-based system. There were people in network management looking at policies, interestingly enough, but that didn't spread. Later on, and today, many of these principles have been accepted. They've been adopted by Puppet and Chef, and then today Kubernetes and systems like this are using policy-based languages to describe systems in terms of constraints. So you have your dynamical basis, and then you have your constraints about what will be promised dependent upon that. And so I developed this thing called promise theory to try to understand how cooperation works between components and systems. And this is turning out to be interesting today with microservices, almost taking this idea and implementing it as a reality. And the key thing to understanding systems when they're cooperative is these three things. There are agents, secret agents, actually just operational things. They could be computer programs, they could be people. And let's not forget that systems are made of people as well as machines. We focus on the software because we think we're in control of ourselves. But actually, the people and how they behave are an important part of any kind of system. So, the agents, the things responsible, we, the people, and the machines, the promises they make, and then the assessments of one another, both inside and outside the system. These are the three sort of poles of the problem. And what promise theory says, is some basic stuff, is that an agent can only make a promise about its own behaviors. I can't make any promise about what you're going to do. Who am I to say? I don't even know your situation. In a similar way, a computer program may hope to goodness that it gets, a certain package delivered from the package manager in time to fulfill its dependency, but if it's not there, it's not going to happen. So an agent can only make a promise about the things it has control over itself. Trying to oblige others, force, expect, you must do this, you must do that. This is the language that computer science tried to use for security, for management, for the longest time, actually. And I think one of the things they managed to show with promise theory is that this is actually an ineffective strategy, because you can dance and stamp your foot and curse and swear, but you can't force something to do something it's incapable of doing or unwilling to do. So cooperation is huge, and of course cooperation between people is even more complex because there are all these emotional things going on as well. An agent can only assess another's promise from its own perspective. So each agent assesses the correctness, etc., from its own perspective. And any reliance or dependency on another sort of invalidates a promise. So if I say to you, I will give you $10,000 if he gives it to me, it's not much of a promise, right? Because I can always say, well, but he didn't give it to me. So you're not getting any kind of promise out of that unless there is also a promise that he will give me the $10,000 to begin with. So dependencies mess up the ability to keep promises in systems. Now, if we go back and look at the history of systems and how they were analyzed for faults, there's a whole statistical branch of science called fault analysis, fault resilience, system resilience. And the way it works is this. In old industrial times, we used to mass manufacture products like light bulbs, or say light bulbs for the sake of argument. After a certain number of hours, the light bulb will fail because it burns through, or so there's some production fault or something like this, and the component will stop working. And because of statistical properties of mass production, there was this observation that if you can more or less guess the rate at which these failures are going to happen probabilistically. Pardon me. And then you can look at a system and say, well, in any system, let's say each component has the probability of failing at a certain time at a certain rate. So what's the probability that the whole system will be working or failing at a certain rate? And you can add these things up according to combinatoric laws and so on. And this is all fair and well, but what it doesn't capture is the idea that we have in the modern world of software that there is a specific function that may be required to be passed on between these things. Not just is it working, is it not working, but what function or what range of values is being provided. What if service is not removed, but simply degraded. To what extent does that affect the outcome of the total system? And when we try to scale and look at the whole picture, what does a traffic jam in one part of Brasilia mean for the flow of traffic in another part of Brasilia? These are the kinds of questions that we need a stronger story about. And this is what promise theory tried to address. The document that I showed you at the beginning is trying to go beyond this sort of simplistic idea of, is it working yes or no, with a certain probability, to what extent do changes affect the functioning of the system. And so to do this, we need some sort of definitions. And I think one of the things I learned in my career is that clear definitions help us a lot to understand what we're talking about and communicate. There's a lot of talk today about, especially in system resilience, we often try to blame humans. It was human error, there was a plane crash or something like this. Even the Delta server problems were blamed on human error, I think. And it's a cheap trick, right? Because at the end of every chain of intent, there is a human that decided something. So you can always trace it back to a human and say it was human error. But maybe that's not the point. Maybe the traffic jam couldn't be attributed to a single person. It has to be attributed to a much more complicated set of parameters. So some clear definitions are helpful. So what does it mean to talk about an error? Was a system in error? So I claim that an error is an action or change whose outcome was assessed not to comply with a promise that it made. If your system doesn't make any promises at all, you can't talk about an error that it made. Now this is really important because we don't talk about the promises much that our systems, we shove stuff together, we make it work, and we're so happy that something is going on, and then we sort of try to use it. But this is not good enough if we're going to talk about there was an error. We need to know what was it designed for, what did it promise. A flaw, so a promise that's assessed to be inappropriate for the intended outcome. So it was, some people like to say broken by design, but was it actually not designed correctly or in a good way to solve the particular purpose? A fault, a state or condition in which the system does not match its desired state. So it's supposed to be this, but in fact it's that. Then it's at fault. But only if it promised. If it didn't promise anything, we can't say it was a fault because it didn't make a promise. So to know that a system is working well, we have to know what did it promise. And instead of talking about was it human error, was it machine error, was it a bug, let's talk about the fidelity of agents in keeping their promises. If they made no promises, they have nothing, there is no blame to be given. If they made a promise and they were unable to keep it, we can talk about the fidelity of the agent in being able to reproduce these promises, to keep these promises over time. And now we're getting somewhere where we can be a little bit more scientific, a bit more technical about whether a system is working well. Riding on top of all of these things, as I said before, is the ability for the system to be stable. And we can talk about the stability, the dynamical stability of a system. Will it crash? If we perturb it with too much traffic, will it just grind to a halt? But then there's also semantic instability, which is whether it stops performing its function or performs a different function at a certain scale or a certain time. These are two different things. They have different causes, and we need to understand the difference between them. But again, having a clear set of promises around these things allows us to make those assessments with much greater clarity. One thing that I did learn over the years is that the idea of a desired state, a desired outcome, on the right here, allows a system to converge to a predictable behavior. Whereas if we're just spawning off things, firing out things in the dark, actually we can't say very much about the outcome because it's diverging in all directions. This left-hand side picture is what you often see in models of system management, firing off new instances to solve problems out of control. This is actually called an explosion. If you did it in any other field of science, we would call this an explosion, an uncontrolled divergence. So then we arrive at the question, okay, so we've got promises, Can we actually say that a system keeps all of its promises and still not be predictable? Sure. If it doesn't make enough promises, or if it doesn't promise the right kinds of things, then clearly we haven't been able to constrain the system or measure the system. We haven't been able to set up measurement sticks around the system in sufficient number to be able to say, would it actually be fit for purpose? So it's not just about having some promises. We have to be sure that we have enough promises going on. Years ago, I got into this business. I started measuring systems. Back in the 90s, we just started measuring systems for months and months and found that they had certain patterns. These are online services. I think the left one is the web. The right one is SMB, Samba services. And you see they fit these beautiful patterns: Monday, Tuesday, Wednesday, Thursday, Friday, not so much on Saturday and Sunday. These patterns have since been reproduced many times, especially by data center engineers. But they show us that a system working well could mean very different things at different times of day. So we need to be able to learn those patterns of behavior and adapt to them, because these tell us that the human working week is the main driver of our systems. The biggest influence causing changes in our system, measurable changes in our systems, is the human working week. It's got nothing to do with CPUs, it's got nothing to do with memory. It's what we do as human beings. When are we surfing the web or sharing files? And each one of these things is a distribution. It's not a value. It's not a critical threshold value as we tend to look at in monitoring systems. It's a distribution of values which varies over time. We tend to assume that things are binary in computer science. Are we above or below some threshold? Who gets to decide that threshold? The happy assessor. And then this, after all of the years of doing computer science, this is still the state of the art of monitoring. Yeah? And what promise is this making? How can we even begin to derive meaning from this graph when we don't know what was promised? And we have no measurement which is saying, yes, a promise was kept or not kept, or which promise was kept or not kept. This has zero understanding of the system. It's like saying, am I giving a good talk by measuring my pulse? Well, yeah, if the pulse stops, we're probably in trouble, but don't count on it. But this tells you nothing about how to improve a service or perform better, or is the system working well? So this is the state of the art. One of the experiments we did with CF Engine was to combine machine learning. This is really old, 90s, so it's really early machine learning. But this kind of measuring these patterns, learning these patterns, and then combining it with short-term, so the short-term behavior of the system, comparing it to long-term measured knowledge, knowing the system as a friend, knowing when it has bad time on Monday morning, by learning repetitively, consistently. This is how we could improve on monitoring, by having multiple inputs with semantics involved, separating timescales, and really sort of getting to grips with the understanding of a system. When I started the CF Engine company, which was in 2008, I didn't think you'd be able to sell configuration management, but I thought the challenge of our time was actually knowledge management. Configuring stuff is relatively simple. It was practically a solved problem, even then. But knowing a system, knowing if a system is working well, that's a hard problem. We can easily stick together a bunch of servers, wire stuff up, install some software, install a bunch of packages, do a whole bunch of configuration settings, and then you step back and you go away on holiday, you come back and you go, oh, how does this work again? How do we understand this monster we've created? It's now misbehaving. And how do we begin to pick it apart and understand it? This is a hard problem. We start at the bottom of this ladder, I call this the knowledge management ladder, we start often in an immature sort of sense of not really knowing what we're doing. We're trying to solve a problem. We're not quite even sure what the problem is, necessarily. So we're sticking stuff together to see what we can do by figuring out how to do it. Later, when we get a bit more maturity, we can separate what we're trying to do from how we're doing it. And at this point, you can become a bit declarative about how you go about it, as we witness from technologies like CF Engine, like Kubernetes in the modern instance, and so on. So separating out intent, what, from how, is an important step in reaching a level of knowledge maturity, because we've done it often enough to know it like a friend. Then later on, if we're lucky, we may understand why we're doing it this way, and we may be able to understand how it could be improved by understanding that why. Far off in the distance, we may actually form goals or understand and reach a state of wisdom, in which we actually know how to do it. And then the way we run the operations side of this depends a little bit on what kind of organization we have to begin with. What resources do we have to begin with? So if we have low organizational maturity down here, then we don't have a lot of internal expertise. We tend to rent services from companies like cloud providers and so on. And then as we grow in our maturity, as we grow in our knowledge, we may actually dial that back and say we need to take over some of this ourselves because these generic cloud services aren't quite good enough for exactly what we want to tune. And then there's the other way of doing it, where you have a lot of internal expertise and you say, I will do it by myself. No one can match my sheer power as an operations person. And so you build it yourself. And then you figure out that doing it yourself on the command line, it maybe isn't as much fun as it used to be after a couple of weeks. And then so you start to automate it yourself, and we kind of end up at this same place through a different route, which is there will be some automated service, partly intended by you, partly delivered as generic services from a commodity provider. And so we climb this ladder of knowledge, and as we do so, we arrive at this sort of equilibrium of self-made intent and generic services coupled together, generic components put together. And so this is our system, a mixture of intent, things we promise, things other people promise, and we try to combine these into a system. How do we know it's working well? We need to know the promises, and we need to be able to assess those promises from different perspectives. See what it looks like in practice. Just to give you an analogy, when we started agriculture, we were hunter-gatherers. We'd run around the forest picking up berries, little rodents or whatever crawling around. There was no farming. We didn't do that. So we started out with human expertise, a huge amount of expertise in, if you look at the hunter-gatherers of Papua New Guinea, or these people have huge local knowledge of all of the different things that they need to do, just like a gray-beard sysadmin knows the systems like friends. And they know exactly what to do, but it's exhausting work. Exhausting work. To scale it up, you need tools. So the first thing, of course, is that we create tools in our own image. We create a giant robot to go around the forest to help us to pick the berries and to catch the mice. And then we realized that actually maybe this design, this human limitation is kind of absurd. Why, if we could do it by machinery, why would we even try to imitate the pain of the human experience? Why don't we just take that out of the loop altogether? And then we move on to a new phase of scaling in which we productize, we commoditize. We don't try to base it on what humans would do. We base it on what's good for machinery, what machinery can do, and try to solve the problem in that way. And when we can take ourselves out of the picture, we can really scale it up because there are no bottlenecks, no semantic disagreements. You can create this gigantic homogeneous array of things. And it's no accident that this hydroponics plant looks like a cloud data center, because the efficient use of space and time when you take human semantics out of the picture, is pretty clear. Regularity, homogeneity. So this is why the knowledge ladder will eventually transform us and allow us to take ourselves out of the delivery picture while still maintaining the intent, deciding exactly what should be on these racks, what the produce should actually be, and whether we are succeeding in keeping our promises. Is the system working well? So then, of course, does it scale? Which is the thing that we're often concerned about. And our understanding of scaling is a little bit primitive in computer science. What we mean by scaling is, can we make it go faster? Can we do more of it? Can we make it bigger? On the podcast that I've been doing with John Willis, we've been digging into this. And actually in my book, In Search of Certainty as well, this was one of the things that I criticized the most, is we need to understand what it means to scale a system better if we're going to succeed at commoditizing a system. Scaling doesn't just mean making it faster, throwing in a load balancer. It means what happens if I increase the size of this part of the system first? What effect will it have on this other part of the system? What is the ratio of this to this, and how does that affect the total promises that I'm able to keep? This is a much harder question to answer than just throw in a bunch of new cores, elastic scale it up, and CPU the hell out of it. But our understanding of scaling in computer science is based on queuing theory, the ability to force more work through a queue. It turns out that this is not good enough to understand the difference between Brasilia and Hong Kong. The scaling models of those things are not queues. They're much more complicated than that. And we need to understand the scaling of systems beyond queuing as well. I did some work this year on smart cities and looking at how cities scale based on the brilliant work of Luis Betancourt and company at the Santa Fe Institute in America. And they found very clear patterns in the scaling of cities. Cities are important, cities are systems, cities are operating systems, just like computers. Actually quite similar to computers in many ways. And we actually have data about cities, whereas we don't have data about computer data centers because it's all proprietary, Google, Facebook these days. The CERNs of computer science are private, so we don't have that much insight. But we can still use scientific reasoning based on similarities of systems to imagine how scaling could work. And this is a subject you can hear more about. We don't have time to go into it this morning, but you can hear more about it in this podcast if you're interested. Crucial thing is to understand that timescales are shifting. Everything is getting faster. And in the olden days, it was very clear we had a separation of timescales which made our management model simple. You had your cron jobs, once a month, once a week, once a day. Then you had your processes. How long does it take to start a server? Maybe half an hour in the olden days. Now maybe a few seconds, or a few minutes rather, for a server. To start a container, seconds. To start a process, milliseconds. To start for a disk access, what is the limitation on disk speeds, read-write speeds? What's the limitation on network processing speeds? As technology develops, all of these things are being pushed up to faster and faster scales, which means that they're closer and closer to the operating system speeds. We built kernels to handle these things which we couldn't do fast enough ourselves. You don't make your interrupt handler with cron. That wouldn't be a good idea. You would be waiting a lot. So we need to have the right kinds of processes to handle the right kinds of timescales. And instead of modularity based on functionality, my message is that we need modularity based on timescales. Slow things shouldn't be holding up fast things. As things get faster and faster, we need to migrate those processes to faster and faster things. This is part of the argument for microservices. But of course, microservices are not a panacea either because they introduce much greater complexity. Speaking of microservices, one of the interesting lessons that I think came out of Netflix rendition of microservices, according to Adrian Cockcroft, is that repairing systems quickly is one of the best things that you can do to know whether a system is working well. You can try to have all kinds of failover redundancy, but that's both expensive and may not work any better than the original thing that you had. So you may be, fighting fire with fire by doing horizontal scaling. But if you can fix things in real time, if you can address faults, errors, and remember these are based on promises that we've made, if you can keep your promises on the time scale at which the promise has to be kept, by repairing it, maintaining it, performing system maintenance at the right timescales, we can keep a system running, working efficiently without failing over, without the expense of additional horizontal scaling. This is the vertical scaling argument. But of course, vertical scaling leads to bottlenecks, it leads to single points of failure, and so on as well. So we also need to balance that against some level of horizontal redundancy. But the rapid repair cycle is important because time always trumps space. Because space, to go somewhere else, to have a failing over to some other place, it always costs us in time, it always costs us in the ability to control something far away. Because remember, we can only keep promises about our own behavior, what is local. We may not get that failover thing actually after all. So, back to the beginning. How do we know a system is working well? This is maybe not as clear as we thought. How many of you think have a different idea of what it means than when you first came in this morning? Okay, a couple. maybe my system could work a little better. It's about these 5 words. To know. Knowledge of a system is about having a relationship between a system curator and its agents. Who gets to know the system like a friend? I saw Marco's no-ops, John Allspor's comment about no-ops being kind of a dumb thing. I have to agree with John on this point, that unless somebody knows the system is working like a friend, then they cannot even say. They cannot curate, they cannot manage, and they cannot adjust the system in some way. So somebody needs to be making this assessment, and that's why humans and that unique ability to learn using actually human skills, knowing like a friend, it's a human skill. It's not a thing you can learn at university. It's our human ability to learn patterns, which allows us as the curators of systems to be an important part of that system in knowing when we're deviating from promises and maybe what to do about it. Knowing all of the little promises made by the different components individually as friends, and knowing, oh yeah, that's probably him not doing his thing, or that's probably her not doing her thing. So we can, by having this continuous knowledge of systems with a continuous interactive loop, we're in a much better situation to know when a system is working well. System, it's a collection of agents collaborating by promises, not ad hoc, not just throwing things at each other as obligations or impositions, events. There should be promises involved. How often is this going to happen? What's the maximum rate at which I will deliver to you? What's the minimum rate at which I will deliver to you? If you can't get service from me, you maybe could get service from somebody else. One of the key things that I learned in service analysis is that if you have a service provider and you've signed up, let's say you've signed up for internet, service provider is unable to keep their promise because some digger goes through the cable outside the house. There's nothing at all the service provider could have done to prevent that digger from going through the cable. It's not able to keep its promise anymore of delivering you the service, but it did its best. Who is responsible for not having service? Is it the service provider, or is it me because I didn't have a backup? Actually, if you follow the logical outcomes of promise theory, it's my fault, because I should have known that no promise can be kept 100% of the time. A promise is not a guarantee, and there are no guarantees. There might be good promises, but they are not guarantees. So if I knew that there was a small chance that service would not be provided and I needed it for a mission-critical thing, it was my fault for not having a backup provider with a redundant route. That's an important lesson from promise theory, I think. Is the system working? Simply means, did it keep its promise or did it not keep its promise? And this applies to each individual agent, each component in the system individually. And is it working well or not working well? Well, we can try to learn, gather statistics, use our human pattern gathering capabilities to make this estimation, but measurable statistics can easily be gathered beyond these primitive monitoring tools that we've come to know and loathe. And if we cannot formalize these questions, these issues, then we cannot even begin to try to answer the question, how do we know a system is working well? So, if you would like to know some more about these things, then I would challenge you to look at some of these other things that I've written. These are in ascending order of difficulty. So you've got your bedtime reading, theory of promises. In Search of Certainty is a sort of historical, scientific, popular science account of scaling, dynamics, semantics, promise keeping, how the whole idea of promises came about, the history of it, and the explanations of it, and where it could be going tomorrow. This one is only if you want to test your mathematical skills or your formal skills. And this one, if you still want to test your mathematical skills and you haven't collapsed with exhaustion from the first one, this one you may find sort of interesting just to see actually the amount of detail and depth into which we can go if we're motivated to tackle some of these questions in a formal way. Thank you very much.